think it's very good that we got into this flow of getting questions during the lecture, and also we'll not have a break after this lecture, so we'll do all the questions kind of on a running basis instead of having questions. Okay, so let me remind you briefly where we left off. We're discussing the O2 model, which is a model of a complex scalar field that has a zero form or a standard conventional phase rotation symmetry that acts on it like this. And I was discussing the two phases. In the phase where the field gets a non-zero expectation value, this U1 phase rotation symmetry is spontaneously broken. So even at that level, the discussion really parallels what happened in the Ising model. We have two phases. They realize the systems, the symmetries differently. Therefore, they're different in the sense of lambda. We know that there has to be a phase transition in between. And much of the story that I told before for the Ising model has an immediate analog in the O2 model. But there's one important difference in the symmetry breaking phase that I want to point out. It's very elementary, and I'm sure many of you know about it, which is that in the Ising model, both phases were gapped. Only the massless point in between was gapless, but both the large positive m squared phase and the large negative m squared phase were gapped. Here, that's not the case, because in the symmetry breaking phase, if you remember the shape of this potential, famously, if you take the symmetry breaking potential and you rotate it around the phase direction of the complex phi field, then you get this kind of wine bottle shape, which at its minimum has a circle. The circle is a set of solutions that all have exactly degenerate energy. In some normalizations, they have the lowest zero energy. And they are the different vacua, the different vevs of phi that are related by the spontaneously broken phase rotation symmetry. That's so far only a little bit different from what happened in the Ising model, but the thing that's really different is that there is a massless particle, there's a massless dynamical excitation associated with this degenerate circle of vacua, and that's the famous massless Goldstone boson. Sometimes people call it a Mambu-Goldstone boson. And, well, one way to describe this Goldstone boson is to basically recognize that the radial mode of the phi field in this symmetry breaking vacuum is massive. So at very long distances, you can approximate the phi field by its vev, but you need to retain the phase. And when you plug that phase back into these functions, V drops out because V doesn't depend on this phase angle, but the kinetic term will give you a massless kinetic term for alpha with no mass term. And so this is a massless particle whose dispersion relation is k nu equals 0 in relativistic terminology, or write the dispersion relation of the frequency and wave number. It looks like that. So there's a massless particle, and there's the famous Goldstone theorem that says that for every spontaneously broken continuous symmetry, you have one such particle. This is in fact a very, very general theorem that can be proven with minimal assumptions, and that does not require a weakly coupled description, so it's kind of one of the workhorses of analyzing strongly coupled systems. Very good. Now, one interesting thing that happens is that in this symmetry breaking phase, if you plug this approximation back into the expression for the current, you'll see that the current becomes some power of V times just the derivative of alpha. So you see that the current is linear in the Goldstone boson field alpha. I just realized that I made a kind of terrible mistake. I really shouldn't have called this alpha. I should call it something else. Because alpha was the symmetry parameter, and I didn't want to confuse it. Let's call it theta. This theta is an actual honest-to-God field. It has an x dependence, and you path integrate over it in the path interval. So you see that what happens in the spontaneously broken phase is that the current, when you act with it on the vacuum, actually gives you directly the Goldstone excitation on top of the vacuum. Because if you act with this field theta on the vacuum, it creates one theta particle. Right? So the fact that the current is linear in theta as opposed to being bilinear in phi is precisely what leads to spontaneous symmetry breaking. Okay, so I think that's, are there any questions about this? I think that's enough about the basic phases of the O2 model. Now what I want to do is I want to make a quick note of some of the features of the U1 symmetry in this model, and then we'll immediately generalize everything to Maxwell theory, or at least we'll get that discussion started. And again, please interrupt. And ask questions while I wipe the board.
Strongly coupled systems always have second order phase transitions?
Not necessarily.
Okay. There's always a massless particle? What was the big?
So the name first order and second order, is essentially a definition. So phase transition is called second order if it has a massless particle. Or more precisely, if the excitation, or more generally, if the excitation gaps close. Right? If you have the vacuum, which is the lowest energy state, then that's what's the next to lowest energy state. And if that gap closes, then you have, roughly speaking, a massless excitation. In a relativistic theory, you would always have a massless excitation. In a condensed matter system that isn't necessarily relativistically invariant, you might not have an actual particle, but you would still have a kind of gapless excitation that comes down. In the first order transition, that excitation gap never closes, it stays finite, and the vacuum jumps below it. Right, so you have a discontinuous phase transition from one. Let me give you an example just before we wrap this up. So in the Ising case, we always had this Z2 symmetric transition, but I can tilt the potential slightly to one side. And or I could tilt it to the other side. Let me imagine I have a parameter that lets me adjust this tilting, right? In this picture, the vacuum is here, and there's an excitation gap. There's no massless particle because this is convex up. And then when you get to this point, there's suddenly two exactly degenerate vacua, but the excitation gaps don't close. Because in each vacuum, you still have a massive particle, nothing massless. And then you go to this picture where there's, again, just a single vacuum with an excitation gap. So in this picture, the excitation gap never closes. And instead, what happens is that you have one vacuum, two vacua, and one vacuum again. And this is called the first order transition. That's essentially a matter of definition. The Goldstone theorem is a theorem. It's not a definition. It's the statement that whenever you sit in some vacuum that spontaneously breaks a continuous symmetry, in other words, if you act with this phase rotation charge on the VEV, like here, it's not invariant. Whenever that happens for a continuous transformation, there has to be a massless particle. There has to be a massless excitation. Other questions? All right. So let me say a few things about currents and charges that I'm sure, again, are quite familiar to all of you, or most of you, but that we would want to then recognize or generalize when we go to higher form symmetries and to Maxwell theory. All right? And so the conventional way, the conventional quantum mechanics physics way of thinking about charges is one takes this conserved current. And one constructs the charge, the conserved charge, sometimes it's called the Noether charge, if you, by integrating the charge density, which is the zero component of the conserved current, over all of space. So I'm integrating over d minus one dimensional space, not space-time. And this is an operator that is conserved, because when you commute it with the Hamiltonian, you get a time derivative, then the time derivative appears in this conservation law. The time derivative of J0 appears in this conservation law, and you can trade it for the divergence of the spatial components. These are the spatial components of J, and this is the spatial gradient. And then if J is sufficiently rapidly decaying at infinity, this integrates to zero because it's just a total derivative by Stokes' theorem. This argument holds precisely when J is sufficiently quickly decaying at infinity. The only case that doesn't happen is when you have Goldstone bubbles. When the charge is basically not so well defined. But this is how you construct the conserved charge out of the current. This is kind of field theory 101. So this is the least sophisticated and the least covariant way of thinking about the charge. Now, there are many upgrades of this formula that I would like to remind you of. And those upgrades almost invariably lead us to the topological defect operators of symmetries that we're familiar with from the kind of generalized symmetry world. And the way one upgrades this discussion is, instead of working in a quantum mechanical Hilbert space, which is, you know, Lorentzian time, and I distinguish time and space and so forth, we can go to a more covariant setting. For example, we might work in Euclidean signature. That's the easiest. We don't have to, but it's certainly the easiest. Wick rotation. And the next thing we can do is we can, instead of just integrating over space, which is a very special choice of three manifolds sitting inside four-dimensional spacetime, or E-1 manifold sitting inside D-dimensional spacetime, we can integrate something over an arbitrary codimension 1 hypersurface, D-1 cycle, and we can try to build a conserved charge associated with that cycle. And the way we do that is we still want to use the current conservation equation, which involves the divergence theorem. So what we do is we integrate the normal component of the current in Euclidean spacetime over this codimension 1 surface. And now if you want to use the conservation equation, this allows you to slightly deform the surface sigma. Because if you deform the surface sigma by a little bit, let's say without doing anything too drastic, just like a small infinitesimal deformation, then the difference between the charges associated with those cycles will be precisely the integral of the divergence of the current over the kind of space in between the two surfaces. Right? So in pictures, you have some cycle like this. You make a small deformation. This is sigma. This is sigma prime. And then in order to get from sigma to sigma prime, you can integrate the divergence of J over this intermediate volume. So the change in the current is the integral of the divergence over the shaded region, and that's zero because of current conservation. So essentially, this shows that, you know, in the absence of any subtleties and other insertions and so forth that I haven't discussed yet, this charge is not just a function of the surface, it's kind of a topological function of the surface, or at least it doesn't depend on small enough deformations within the same homology class. So when we have a U1 symmetry, right, it's perfectly fine to work with the charge Q, but for the purposes of generalization, it's often useful to exponentiate that charge. So sort of working sort of with the Lie algebra, we can exponentiate and work directly with the group-valued symmetry charges. And those are obtained by taking an angle, alpha, and then you can exponentiate the charge. And of course, this thing still depends on a surface. So these U operators depend on a choice of angle alpha and surface sigma. This angle alpha parameterizes a U1 group element, and this dependence on the surface sigma is topological. So this is the simplest, kind of most elementary setting in which you can see the emergence of these group-valued topological defects or operators. Here they're codimension 1 defects, and that's related to the fact that we're discussing an ordinary zero-form symmetry. Once we go to generalized symmetries, we'll encounter topological defects of other dimensions. And of course, in this case, it's very elementary, but because the group is U1, but you can easily check that these operators satisfy the group law. And otherwise, if you multiply two of them with different phases or different angles, the angles will combine. So you get these kind of group-valued codimension 1 topological surface defects. In this case, they simply follow from the existence of the conserved current. So they're simply a restatement of something that is already very standard and very well known. But the virtue of this presentation, of course, is that it generalizes dramatically to situations where we don't necessarily have such a current. Or maybe we still have a current, but the current looks a little bit different than this. Now, there's one last thing I need to tell you, which is something we'll also look for in the generalized symmetries world, which is, so we would like to understand in these different presentations how we figure out the way in which the symmetries act on the other operators in the theory. And in particular, we would like to understand how it acts on the charged phi field. Right? The thing we started our discussion with is that we would like our phi field to enjoy these U1 phase rotations, and somehow that has to do with how this charge Q acts on phi. And in the usual quantum mechanical presentation, as I said, working in a Hilbert space and choosing time and so forth, one takes this charge here and simply computes its commutator with phi. And you can do this explicitly using this formula, using the canonical commutation relations of phi and phi dot. Phi and phi dot don't commute. They have a delta function commutator. And what you find is that you get, well, in general, you get I times Q times phi of x, where Q is precisely the U1 charge of phi. In this case, that's 1. Q is a C number, not an operator. And it's just the charge of phi. So this is the kind of old, let's call it old-fashioned way of computing the charge. The more sophisticated way of computing the charge is to use these topological codimension 1 defects. And the way to do it is you take the operator phi in Euclidean signature, and then you encircle it with this codimension 1 defect. And so the fact that the operator lives at a point in space-time and the defect is codimension 1 means that these things have non-trivial kind of linking, right? The surface links this point. And precisely when this happens, this surface integral can be non-zero. So you can extend this integral into the bulk, if you wish, by writing it as a divergence of J integrated over the interior of the ball. Then you can again compute how that divergence of J acts on phi. And what you find is, again, the same formula. And of course, if you do it with the U's, you'll just get the exponentiated version of this. But This is the difference between the Lorentzian and the Euclidean presentations. In Euclidean signature, we link the charged operators with the topological symmetry defects. And that will be the thing that also generalizes higher form symmetries into more general categorical symmetries. Any questions? Okay, very good. So let's take stock a little bit of what we've done here. I can also tell you a little bit of what we haven't done. We haven't discussed so much the space-time symmetries associated with the stress tensor. It's an analogous story to what I said for those. And there's also an analogous story to what I said for discrete symmetries. For example, the Z2 symmetry of the Ising model. The only thing you don't have in the discrete case is the current J, right? But you still have the final output of this construction, which is the, group valued exponentiated version of the symmetry. So once you have arrived at this point, you can do these manipulations even though there's no carbon. Okay, so this is a very brief review of a very simple model with a lot of physics, and then there are many other models with lots of symmetries that have been studied over the years or the centuries by now. And symmetries are incredibly useful. I don't have time to sort of give you a representative sample of all the wonderful things they can do for you. But the point is, it's not a new idea that one should try to generalize symmetries, and that one should find as many symmetries as possible to analyze interesting physical systems. And over the years, people have attempted different forms of generalizations. And sort of it's historically a little bit interesting to understand where the higher symmetries and the categorical symmetries that we study now sort of come from in this bifurcation of generalizing symmetries. All right, let me here. So there's an interesting fork in the road. Started emerging maybe in the 60s or so. And first people took one fork, and more recently they took the other fork. And roughly the question is, how do you generalize this? So we've discussed zero form symmetries with conserved currents, which are vectors or one forms. And I've also briefly mentioned that in relativistic systems, at least, there's a conserved symmetric tensor, which is the stress tensor. So this leads to space-time symmetries, like translations, or in relativistic systems, Lorentz boosts. And those symmetries are generated by a conserved symmetric tensor current. And the question is, how should one generalize this incredibly successful machine for making symmetries and for using them? And the obvious generalization, if you look at these two examples, is that you should study conserved operators of higher rank that are symmetric tensors. So based on these two examples, there's an incredible amount of literature studying models that have conserved currents of this form. These are sometimes people call them higher spin currents. So there are symmetric tensors of rank greater than 2. There could be other rank 2 tensors as well. Doesn't really matter. And they obey a conservation law like that. That would seem to be a natural generalization. And indeed, such currents do arise in interesting, special, two-dimensional models. But it turns out there's more or less a theorem, I mean, a physics theorem, that says that models that have these kind of currents are necessarily integrable. And that means that they can be, roughly speaking, of two varieties. They can either be interesting, which means they have to live in 2 dimensions, or they can be boring, which means they can live in more than 2 dimensions, but they have to be free. And there are different ways of thinking about this, but roughly speaking, this goes under the slogan of the Coleman-Mandula theorem. The Coleman-Mandula theorem is something one often hears about in the context of supersymmetry and the history of supersymmetry. It's not a statement about supersymmetry, it's in fact a statement about bosonic symmetries. And it's the statement that these higher spin conserved currents give rise to such powerful symmetries that they essentially, they want to make the quantum field theory that has those symmetries free. Roughly speaking, the reason for that is that if you think of the conservation laws associated with the stress tensor, they are, roughly speaking, momentum conservation and angular momentum conservation. And momentum conservation and angular momentum conservation give you constraints on the scattering amplitudes of your particles, right? If you look at 2 particle scattering and you would take out angular momentum conservation and momentum conservation, there's still one thing left over, which is a function of the scattering angle. There's a non-trivial function of the scattering angle, which means that the amplitude for scattering, the probability for scattering can be non-zero. Two scattering in physics is in general not trivial, even though angular momentum and momentum are conserved. If you have these conservation laws, they give you more conserved quantities that depend on the momenta of the particles you scatter. And in general, they're also nonlinear polynomials of the momenta. And that basically means that the scattering amplitude is trivial. So in these models, you don't have scattering. There's precisely one loophole, which is factorized scattering in integrable 2D theories. So this is a very interesting path, but it's not the path we'll talk about. Yeah?
State again exactly what are the assumptions and what's the conclusion of the theorem?
Well, the context in which Coleman and Mandula proved it was that they were considering gapped quantum field theories, relativistic quantum field theories, in which the S matrix exists. So something like massive phi to the 4th theory or something like that, where there's absolutely no infrared subtleties associated with the S matrix. So for example, you could consider proton scattering in QCD or something like that. Then this is a completely healthy object. And they prove that if you make this assumption that the S matrix exists, and on top of it, it satisfies various standard analyticity properties, which in relativistic quantum field theories are known to follow from essentially Lorentz invariance. You know, the standard kind of microcausal structure of commutators in Lorentz invariant theory is the statement that 2 operators commute if they're space-like separated. That assumption, plus the existence of these conservation laws, then shows that the S matrix is trivial, at least in more than 2 dimensions. So these analyticity properties are not easy to prove, but if you just assume them as they did, and at the time they were assumed to be universal and hold in all quantum field theories. Now we know that there's subtleties in massless theories and gauge theories and all. But if you have a nice gap theory without any massless particles, then I think these assumptions are pretty safe. there's a much more modern and recent version of the theorem which is supposed to apply to massless theories, and in particular to massless theories with conformal symmetry. In that case, one can replace the S matrix, which doesn't exist in these theories, with correlation functions of operators, and in particular conserved currents. And in those theories, Malatena and Jiboirov showed maybe 10 years ago or so, maybe 15 years ago, that the same conclusion holds. That in more than 2 space-time dimensions, conformal field theories that have these higher spin conserved currents are free theories. So they have trivial S matrix, Gaussian correlation functions. So what is the loophole or the alternative that the thing being loosely speaking called generalized symmetries or higher symmetries exploits? How can one get around this? Any generalization of Lorentz invariance or normal internal symmetries in Lorentz invariance leads to a trivial S matrix. That would be very boring and very bad, and we would not be so interested in these. But it turns out that that's not true, because it turns out that the generalization that's involved in going from here to higher form symmetries is not via symmetric tensors, but via anti-symmetric tensors. And as I'll explain in a second, that means that those symmetries do not act on the S matrix. So there's a very simple loophole in this theorem, which is that some symmetries don't act on the S matrix. And in the 60s, when this theorem was proven, that was not appreciated, but now we appreciate it. And there's lots of interesting examples. And all higher form generalized symmetries fall into this class. And the basic reason for that, and you'll understand the reason in 10 minutes, is that the conserved charges that come out of higher form symmetries simply do not act on the particles that you scatter when you ask about the S matrix. The S matrix is a question about scattering point particles. Particle 1, particle 2, you set up the initial state and then you let it evolve. But if all you know about in the universe is point particles, then you will essentially never learn about generalized symmetries. All right. So how does this work technically? Technically, the magic is that it's also interesting to consider higher form currents. So currents that also have many indices, but that are totally antisymmetric. Here's an N form. And we can impose conservation laws. These are the things that are called higher form symmetries. The things that come from such totally antisymmetric conserved currents. And in the conventions that I've been using, where I've been calling the thing that comes from this current a zero form symmetry, something that comes from a conserved n form current would be n minus 1 form symmetry. And depending on which space-time dimensions you're in and which models you study, you will encounter all of these form degrees. But usually, by the usual magic of Poincare duality in a given dimension, the interesting forms stop being interesting dimension. So for example, when we study gauge theories in 4 dimensions, the most interesting higher form symmetries that we'll encounter will be 1 form symmetries. Very rarely 2 form symmetries. All right. So these higher form currents are the simplest, most naive, and also most explicit generalization of the story, the standard story I reminded you of before, to generalized symmetries. And that is one possible entryway into the subject. So now I'm going to give you the canonical example of an interesting theory that has this, which is free Maxwell theory. Any questions about this general discussion? Yeah.
So this higher form symmetry only works when you consider this this equation motion when you.
Sorry.
So I think this conservation of higher form current is only works when you consider the equation motion on shear approximation. When you
That's even true for ordinary symmetries.
if you consider quantum fluctuation, maybe there is some violation.
A couple of things. Okay, so first of all, even for ordinary currents, current is only conserved on shell, meaning you have to use the equations of motion. That's true even classically. In quantum field theory, generally speaking, the equations of motion also hold. Then there's interesting fine print. Sometimes they're modified, but more, the baseline is that if you look at an operator like this and you stick it in a correlation function away from other operators so that they don't collide, then the classical equations of motion also hold quantum mechanically. So 99.999% of the time, the current operator will be conserved. Then there are the interesting exceptions. Whenever an exception occurs, we call that an anomaly. And they're very interesting because they're extremely rare and extremely rigid. And the reason we focus all our attention on them is because they are analyzable. But the norm is that, that the symmetries that you study are not anomalous. And in that case, the classical conservation equation also holds quantum mechanically. That should be your baseline. And there was a different question there.
When you see that these higher form symmetries do not act on the S matrix, you're assuming that the asymptotic states are not created by lines or surfaces? Or
That's the conditions under which a conventional S matrix exists. You know, like in order for the S matrix to exist and satisfy all the assumptions that Coleman and Mandula wanted it to satisfy, you really need a theory that's kind of a little bit boring, like a non-gauge theory, completely gapped, no long-range forces, no topological field, you know, like something like massive phi to the 4 theory would be a good example. Or if you wish, QCD, you know, with massive quarks, so that you only have massive protons, massive neutrons. Those are the conditions in which the S matrix A exists and B satisfies a lot of nice properties. The moment you have massless particles, it's already in trouble because of infrared divergences. Then on top of that, what you said becomes true, which is you might have states that are created by extended operators, and then they modify the braiding or the you know, kind of Bose exchange rules of the particles. There's all sorts of things that you need to worry about, and in fact, they do matter. Yeah. So these vanilla arguments only apply to cases where those issues don't come up.
In this very example that you just mentioned of QCD, where the quark state would be created by the local field attached to some line to make it gauge invariant?
The quark state doesn't exist in QED. If you act with
QCD, or the electron QED.
I mean, the quark state is infinitely heavy. QCD, we have
electron in QED.
The electron in QED exists, and we measure it. In fact, in order to make sense out of the electron as a state in the Hilbert space, you have to act with a gauge invariant operator of the vacuum to create it. So you have to take the electron field, you have to dress it with something usually a Wilson line or something else.
Yeah, but the question is, doesn't then this line affect what you say?
It doesn't affect everything. The QED S matrix doesn't exist, and since it doesn't exist, the fortiori doesn't satisfy any interesting axioms. So, yeah, even in QED, there's lots of problems with just trying to apply some general S matrix argument out of the box. Okay, before we get to QED, let's discuss free photons. That is much safer, and it's still pretty interesting. this is the historically prototypical example of gauge theories. It came first. And but nevertheless, we still learn new things about it, so that's nice. And it is the prototypical example of a theory with continuous higher form symmetries. For those of you who are familiar with theories in 2 dimensions, there's the theory of the compact boson, which has many, many formal analogies with Maxwell theory in 4 dimensions, so I'll sometimes point them out, or you can also ask about them if you want. I'll continue working in Euclidean signature so that we can keep drawing these nice topological defect operators, and that will lead to some unfortunate factors of I, but the unfortunate factors of I are actually essential because they encode some interesting physics. They're unavoidable in Euclidean signature, though. Very good. So let me discuss some basic aspects of Maxwell theory that I will need. The action, at least in flat space-time, let me consider for starters just flat space-time. And I'm also going to limit myself to 4D. There's lots of nice generalizations if you look at other dimensions, but let's stick to 4D. And I'm going to write the action as a function of a one-form connection, which I'll explain what it is in a second, in the following way. So and I'm going to try to write some actual formulas. And this is the standard Maxwell action. I'll write it in 2 different ways, and then I'll explain what the different symbols mean. These 2 different ways of writing it are the form way and the kind of more old-fashioned component way, which are useful. I'm going to use these kind of superscripts to distinguish different form degrees when I don't explicitly write indices. So for example, this will be an n form. And this A1 here is the standard gauge connection. So this is A mu, which is the Maxwell gauge field. And F is its field strength. F is a 2 form, which is dA. So that's the thing that encodes the E fields and the B fields. All right. So one of the most obvious ways to see that Maxwell theory has something to do with higher form symmetries is to remember that dF has to be 0 by the usual Poincare lemma, because it's dA, and so d squared is 0. And since F is a 2 form, we immediately get, with essentially 0 work, an example of something that should be thought of as a Poincare. Actually, this is a closed 2 form. If you want to build the associated conserved current, you can take the hot star. We'll do that in a second. So this just comes from the fact that F is dA. There are also equations of motion. We discussed before that in general, conservation laws for currents only use the equations of motion. Here's a counterexample to that statement. This conservation law holds even off shell because it just comes kinematically from this fact. But there's another conservation law, which is the equation of motion associated with A. Right? And when you vary this action with respect to A, what you find is the other Maxwell equation, or the other pair of Maxwell's equations, which is the statement that d star of F is 0. So in components, this is the statement that the divergence of F is 0. And this is the thing that is usually called the Bianchi identity. Okay, very good. So we already had in this model conserved 2 forms, so that is good. We're on the right track. We'll discuss them in a second. But now I'm going to have to talk a little bit about gauge theory, gauge symmetry, since this is a gauge theory. So in the spirit of what I said at the beginning of the lectures, let me call it gauge redundancy. This is a U1 gauge theory. So there's a U1 gauge. Let's see. And that acts on A in the usual way. Shifts A by d lambda. And this lambda is just, it doesn't have any form indices. So it's a quote-unquote function of space-time if you write it out, but it's not really a function because it itself has transformation rules, non-trivial transformation rules. And instead, it's a circle-valued parameter. So one way of describing it is that you identify the target of lambda by 2 pi, so that it's a circle-valued function of space-time. Okay. And it's precisely this statement that lambda is not a well-defined function of space-time into R, but instead a circle-valued function that makes this U1 gauge theory. We took lambda to be a well-defined R-valued function of space-time, then that would correspond to R gauge theory. And even though R gauge theory and U1 gauge theory have many similarities, for example, they both have a photon, their global properties and their topological properties and their symmetries are very different. So U1 gauge theory is the standard version of the theory that we study, and that's the one that we're going to discuss.
Sorry, the plus 2 pi belongs into the argument of lambda, right?
Argument of lambda.
Sorry, never mind.
So x is a function, so lambda is a function of spacetime into U1. Other questions? Very good. So one of the interesting consequences, so these transformation rules mean that A is a standard U1 connection. When one studies abelian gauge theories, there are variants of U1 connections that one encounters, spin C connections, blah, blah, blah. But this is a standard garden variety U1 connection, the way you encounter it in differential geometry, and that fixes the transformation of lambda. And this fact immediately implies that the fluxes of F are quantized, that F has quantized electromagnetic fluxes on closed 2 cycles. So if you compute 1 over 2 pi times the integral of F over a 2 cycle, then that has to be an integer.
Is it not always 0 the way you set it up?
Nope.
F is d8, and then
Right, but A is not a globally defined one form. A is a U1 connection.
yeah,
So I was just about to ask whether everybody knows why this is true. So I think the question answers that. So let me briefly explain why this is true. So this is a very general fact, but in its simplest incarnation, when sigma is just a 2-sphere, this is the original argument due to Dirac. This is what's called Dirac quantization. So let me explain why, in general, the fluxes can be non-zero. This is precisely the difference between U1 gauge theory and R gauge theory. So let's compute, let's do what you suggested. Let's compute the integral of F by writing F as dA, and then we can cut the sphere into hemispheres, into 2 patches, north and south. And we can write the integral of F over the sphere as, this is dA. So essentially we can pull it back to the boundaries of these patches. Right? So we have the integral of A from the north patch minus the integral of B of A from the southern patch. They have opposite orientations. And these boundaries coincide. That's the equator of the sphere here. You can make them overlap if you want to be more sophisticated, but this is sufficient. And indeed, naively, this is 0. But in fact, look at the transition region that contains the equator. the gauge field in the northern hemisphere and the gauge field in the southern hemisphere might not be trivially identical. They might differ by precisely such a gauge transformation. Right? And that's what happens in the presence of magnetic flux. So here you have A north, here you have A south, and they might differ by d lambda in this equatorial overlap region. So this is the integral of d lambda over, roughly speaking, the equator. Now, if lambda were an r-valued function, this is 0, right? But since lambda itself is circle-valued, or in other words, it can have winding, this is nothing but the degree of the map from the equator to the u1 that's specified by lambda. And that degree can be any integer. So you can consider gauge fields in the northern and southern hemisphere that in the equatorial region need to be glued by a lambda that has arbitrary winding number around the equator. And this winding number is precisely the magnetic flux. Sorry, I forgot a 2 pi. This is 2 pi. Yes, because the conventions for my lambda, these are the standard physics conventions. They're annoying, they have 2 pi's everywhere, but we live with them. And that means that the integral of f is 2 pi times an integer. Does that answer your question?
We still doesn't work on that for. You need to remove a point.
Of course. Yeah, of course, you need to introduce a 2 cycle. But even in R4, we do that. I'll explain that in a second. So in R4, you have to introduce a defect, then you remove a point, or you can just work on a manifold that has geometrically already a 2 cycle in its topology. But the point is that one way or the other, U1 gauge theory has admissible fluxes. They're part of the theory, and one should study them. If one doesn't study them, one is blind to precisely those things that makes the theory U1 gauge theory, as opposed to R gauge theory. Very good. That's roughly speaking the old-fashioned point of view of U1 gauge theory, which is that it's just a theory of photons in R4, and you can't say anything interesting about the fluxes. But very good. All right. So we're almost running out of time, but I think I'm also reaching a decent stopping point. So the theory has fluxes, and tomorrow we'll discuss the operators that create and destroy these fluxes, and we'll see that precisely those operators are charged under the higher form symmetries of the model. Let me make a small comment about the gauge coupling in this model. Very often in presentations of free Maxwell theory, one sees the statement that it's possible to absorb the gauge coupling by rescaling f. So the gauge coupling is not a meaningful parameter in this model. But this is not correct. It's not correct precisely because the fluxes of f are quantized, or the winding of lambda is quantized. And if you rescale the gauge field in order to absorb the gauge parameter, then you formally remove it from the action, that's true, but it pops out in these periodicity conditions. So then the fluxes of f would now be valued in something like 2 pi e squared instead of 2 pi integers, and the winding of lambda would similarly involve an e squared. So the e squared doesn't disappear, it just moves around. So even free Maxwell theory has an e squared, and indeed you can compute correlation functions of certain line defects that depend on e squared. We'll do that tomorrow. That's comment number 1. Comment number 2 is that, of course, I started the discussion by saying that we just take space-time to be flat, but already implicit in the discussion here of the S2 was that we would allow, in principle, a space-time to be any nice Riemannian manifold. In general, you might want it to be an oriented manifold, but in free Maxwell theory, you could even take it to be unoriented because the theory enjoys time reversal symmetry, so time reversal symmetry also allows you to consider unoriented manifolds, but for the purposes of what I'll discuss, I'll take M to be an oriented Riemannian manifold. And so you have to choose a Riemannian metric, but that's not a problem. You can do that in the standard way. This way of writing it makes that obvious. And it's also interesting to ask how the properties of the theory depend on that Riemannian metric, how they depend on the topology of that manifold, and so on. So some of that we'll discuss tomorrow when we flesh out the higher form symmetries of this model and the various observables. Since I only have 2 minutes left, it's a good time to ask for last questions. Any last round of questions?
I guess, could you speak a little bit about, like, morally what the role of defects is? Like I've seen examples, but like why have we collected all these into one category of things?
Sorry?
Why have we collected all these sort of disparate phenomena of introducing topological submanifolds, and what do we call these defects?
Well, okay, so I can speak just a little bit to the name. So we'll encounter defects tomorrow. And not all defects are topological. Defects are any kind of insertion into the path integral, any kind of object that you study that is localized on some submanifold of spacetime. So these are, local operators are kind of point defects. Then we've already seen topological hypersurfaces, but there'll be defects in between. For example, there'll be line defects, there'll be surface defects. Not all of them are topological. The word defect is used, sometimes people use it interchangeably with operator. They just use it to mean insertion or observable in the path integral. And in general, the word is used with some notion of locality attached. So you want to talk about defects of a certain dimension or codimension. So first of all, the two important aspects. First of all, they exist. So if you're interested in the physics of this model, you better study them. It's not a choice. The second question is, what are the principles that organize them? How do they talk to each other? And this is where the higher symmetries come into play. So we'll see explicit examples in this model tomorrow, and then in other models.